Welcome to the deep dive. You've sent us the sources, and today we are tackling, well, the world of decisions. We're moving beyond predicting those continuous numbers, things like how much or how long. And we're focusing on that really decisive question, yes or no.
That's right. And that's a totally different ballgame. When your desired outcome is strictly binary, admitted or rejected, successful or failed, you can't use the standard linear tools.
You can't, so you need something else.
You need logistic regression.
So our mission today is to really get under the hood of this crucial statistical tool, and I think most importantly, learn how to translate its often opaque output into clear, actionable insights.
And we are using a fantastic real-world scenario to guide us through this. Our sources give us data on 400 candidates for graduate school.
Okay.
And we're looking at how their GRE scores, their GPA, and the prestige of their undergraduate institution, which the data calls rank, how all that influences their probability of getting that acceptance letter.
So for you listening, the question is, based on these factors, what are my true chances of success? Let's dive in.
Let's do it.
All right, so if you've worked with standard linear regression, you know the formula. It's that classic y$ equals beta 1x for 1, and so on.
Yep.
And it works great for predicting something like, say, a housing price. But if we try to use that same formula to predict a binary outcome, like admission, which is a 0 or a 1...
The model could predict anything.
Anything.
It could predict 10 or -5. And what does a -5 chance of getting into grad school even mean? It's statistically nonsensical.
It's meaningless.
Right. So we need some kind of mathematical fence to make sure our predictions always live between 0 and 1, between 0% and 100%.
Okay, so how do we build that fence?
Well, we turn to something called the General Linear Model Framework, or GLM for short. And it introduces this really clever piece of math called the link function.
A link function.
Think of the link function as a translator.
Okay, a translator. I like that.
It takes the linear prediction part of the model, which, as we said, can run from -infinity to +infinity, and it transforms it. It squishes it into the probability we care about, which has to be between 0 and 1.
And for logistic regression specifically, that translator has a name. It's the logit link function.
Exactly. And the logit function is sigmoidal.
Which means S-shaped.
S-shaped. And that S-curve is absolutely key. It's what ensures the predicted probability changes smoothly. It avoids those sharp, impossible jumps outside the 0 to 1 range.
So it gives us a continuous, sensible prediction of admission probability.
It's just a really clean way to map our inputs, the GPA, the GRE, the rank onto a meaningful probability curve.
So what's happening under the hood? What does that S-curve really represent?
Well, the math essentially assumes there's an underlying unobserved continuous drive. You could think of it as maybe the candidate's true motivation or their raw potential.
A latent variable.
A latent variable, exactly. And the model says that if that unobserved score crosses a certain threshold, the outcome flips from 0 to 1. You get admitted. The S-curve is what links our measurable data to that hidden drive.
Okay, that makes sense. We've built the S-curve. Now we have to figure out how much weight something like GPA carries versus, say, the GRE.
Right. And for that, we use the maximum likelihood method to estimate the model parameters. It basically finds the coefficients that best explain the data we actually observed.
And this is where we hit what the sources call the interpretation wall.
Yes. This is it. Because the coefficients in our model output, those estimated est values, they do not represent a direct change in probability. They can't.
No. They represent the predicted change in the log odds of the event happening.
The log odds.
And I think that's the point where most people just throw their hands up. I mean, log odds. Why do we even bother with that if the goal is just simple, intuitive probability?
That is the essential question, isn't it? And the reason statisticians stick to the log odds, at least at first, is, well, it's purely mathematical.
Okay.
It's what allows the relationship between the predictors and the outcome to remain linear. We need that linear structure to calculate the coefficients accurately. If we tried to use probabilities directly, the estimation math would just become exponentially more complicated.
So the log odds keeps the calculation clean, but the interpretation is messy.
Precisely. The coefficient for GPA, for example, tells us the change in the logarithm of the odds of admission for a 1-unit increase in GPA, which is
That's mouthful. It's dense.
It's very dense information.
But here's the key takeaway. This is the translation step we were talking about.
Yeah.
We can convert that messy log odds coefficient back into the beautiful intuitive odds ratio.
And it's so simple to do. You just exponentiate the coefficient. You take into the power of the coefficient.
So e to the coefficient. And that gives you the odds ratio.
Right. And the odds ratio is the factor by which the odds of admission change when your predictor increases by 1 unit. This is the language of practical insight.
And the rules are incredibly simple. I love this part. If the odds ratio is greater than 1, the odds of success increase.
Yep.
If it's less than 1, the odds decrease.
They go down.
And if it's exactly 1, that variable is essentially irrelevant to the outcome. It immediately tells you if GPA is helping or hurting, and by how much.
Exactly. And even though the calculation involves all that log odds stuff, the resulting odds ratio is consistent across the entire range of scores. It makes it a really reliable measure of impact.
Okay, let's apply this. We have our admissions model. It's based on 400 applicants. The sources say the model is strong, statistically significant overall.
Yes, it's a good model. We're using the LogitLink function we just talked about. Let's dig into those odds ratios.
Let's start with GPA. What's the coefficient?
Starting with GPA. The estimated coefficient is a highly positive 0.80, and it's very statistically significant.
Okay, so 0.80, let's translate that. So we take $1 to the power of 0.804.
Which gives us an odds ratio of approximately 2.23.
Wow, 2.23.
It's a staggering finding, really. For every single additional GPA point a candidate earns, the odds of them being admitted more than double.
More than double.
That confirms GPA is a true power player in this whole admissions process.
All right, now for what I think is the shocker. The GRE score.
Right. So the GRE is technically statistically significant, has a p-value of 0.04. So the model confirms it has some effect.
Okay, it matters a little bit statistically.
But the estimated coefficient is minuscule. It's 0.002.
0.0002.
So when we exponentiate that tiny coefficient e to the 0.0002, we get an odds ratio of 1.002.
1.002. So a factor of 1.002. What does that mean in plain English?
It means that a 1-point increase in your GRE score increases your odds of admission by a measly 0.2%.
0.2%. That's nothing. You could score 100 points higher on the GRE, and the practical boost to your odds would still be tiny compared to just moving your GPA by 1/10 of a point.
It's nothing. And this is just a perfect demonstration of statistical significance being completely divorced from practical significance. The GRE technically matters, the math says so. But practically, the admissions committee is barely registering the difference.
This raises a really critical question then for researchers, for anyone building these models. If a variable has almost no practical predictive power, is it even worth including?
Exactly. And that's why our sources bring up concepts like the Akiki Information Criterion, or AIC, and the Bayesian Information Criterion, BIC.
AIC and BIC, what do they do?
They're measures used specifically to evaluate that balance between how well the model fits the data and how complex the model is. They actively penalize complexity.
Oh, interesting. So if the GRE variable adds complexity but only returns that tiny 0.2% gain in predictive odds?
AIC and BIC would likely scream at you. They'd say, simplify the model, get rid of the GRE.
It's just adding noise.
Precisely. Better to have a simpler, more robust model that's focused on the variables that truly move the needle.
Okay, that brings us to the last one. Let's look at the institutional prestige, or rank.
Right.
So in this model, rank 1 institutions were used as the high prestige baseline, so everything is compared against that.
Exactly. So we're looking at how institutions of rank 2, 3, and 4 stack up against that top tier.
Yeah.
And we see a major difference here.
Okay.
For students from a rank 2 institution, the coefficient is negative 0.68.
Negative, so that's not good.
Not good. And the odds ratio is 2 baller to the negative 0.675, which comes out to about 0.51.
0.51, so half the odds.
Half the odds. Holding GPA and GRE constant, just by attending a rank 2 school, your odds of admission are cut approximately in half compared to someone from that rank 1 benchmark.
That's a huge effect.
It's massive. And it accelerates dramatically for the lower ranked institutions.
Yeah.
The rank 4 coefficient is negative 1.55. which is the strongest negative effect on admission chances in the entire model.
So the story the model tells is crystal clear.
It really is.
GPA is your strongest positive driver. Undergraduate institution rank is a powerful gatekeeper. And the GRE score, despite being technically required,
Is practically negligible in determining the actual odds of you getting in.
And the only reason we can say that so clearly is because we did the translation.
Exactly. That translation from the confusing log odds to the intuitive odds ratio allowed us to move from just statistical noise to practical truth.
Okay, so we just completed a really crucial deep dive into binary prediction. We extracted some key knowledge on why we use that S-shaped logistic curve to keep our predictions sane, and how we navigate the challenging language of log odds.
And remember these key takeaways for your next binary modeling challenge. First,
If the outcome is yes-no, you need logistic regression, probably with the logit-link function.
second, the model uses log odds for its internal math, for the linear estimation, but you must convert that to the odds ratio to the beta for any intuitive interpretation.
And third, and maybe most important, always contrast the statistical significance, the p-value, with the practical impact, which is that odds ratio.
See if a variable truly matters in the real world.
And that brings us right back to our conversation on model efficiency. We saw the GRE score was, technically significant, but it delivered an almost irrelevant gain to the practical odds, that 1.002 number.
So that leads to a really interesting question. If you, as the researcher, are using assessment metrics like AIC or BIC,
Right.
which strictly penalize model complexity,
Right.
how do you defend keeping a variable that is statistically verified but is, for all intents and purposes, practically irrelevant?
That's the ultimate question for model building, isn't it? Does this tiny verified contribution, this 0.2% increase in odds, justify the increased complexity, the computational overhead, and maybe even the data gathering cost of including that predictor in the first place?
That is the balance. It's the balance you have to strike when you decide what ultimately belongs in your final predictive model.